Hello everyone, I hope you are all fine. During the last two sessions, we talked about the definitions in structural analysis. We talked about equations of equilibrium, and we also talked about how to find out or how to understand whether the structure is stable or unstable. We also talked about the situation of having a determinate structure or an indeterminate structure, and we said if the equations of equilibrium can be used for finding all the reactions in a structure, that the structure is externally stable and determinate. But if a structure is indeterminate, we cannot use the equations of equilibrium to find all the reactions on the structure. So today we are going to look at a few example problems, and I'm going to show you how to use those procedures and how to first find the reactions and understand whether a structure is determinate or indeterminate. Usually if I wanted to write these on a board and if we were to solve these together, it would take a little bit of more time, but just showing them on a file and reviewing the solution process will take less time. So we are going to have a few minutes at the end of the class, and what I want you to do is to use that time for solving these examples on a paper, and I will also provide a link for video call. So after explaining the solution procedure, you can start solving these yourself. And if you face any problem or if there is any question about the solution procedure, don't hesitate to use that link to start a video call with me and we can discuss the solution over there. Or if you want, you can send me an email and we can discuss the problem and issue or whatever situation that you are facing during the solution. We can discuss that through email. But let's see how we should find the reactions in structures and how we can understand whether a structure is determinate or indeterminate. So let's take a look at the first example and see how we can find these reactions and basically do the structural analysis for this simple beam over here. As you can see, the question is saying determine the reactions at the supports for the beam shown below. So we have to find the reactions in this beam. I'm going to mention the general steps for each example, and I expect you to follow these steps in your solutions for homework problems and exams too. So you have to find the reactions. The very first step in finding the reactions is to draw the free body diagram, meaning you have to draw the structure, put all the forces, and also put the reactions that you have at each of the supports on the structure. Over here we have a roller support on the left, which is not completely horizontal. It has an angle with respect to the horizontal line, and also we have a hinged support over here on the right side. So based on the definition of these supports, we know that for a roller support we only have one reaction, and that reaction is perpendicular to the plane that the support is located. Over here we have this roller support, and I know there is going to be one reaction, so this is the reaction and it is perpendicular to this plane which the support is located on. For the hinge support over here, we know that we are going to have two reactions at the place of hinge support, and those reactions are shown over here. By, the vertical component, and Bx, the horizontal component. And as you can see, I have the 12 Gibbs force over here, which has an angle to the direction of the beam or to the horizontal direction, and I have a 6 Gibbs load located at the end. So this is the free body diagram of the beam or of the problem. The second step is to understand the determinacy or indeterminacy of the beam. We have to remember and use this equation as we talked earlier in the presentation files. Just put the values instead of the parameters and then check the value of I and see whether it is smaller than 0, equal to 0, or greater than 0. So let's see what are the values in this equation. R is the reactions that we have in the structure. In this case, for this beam, I have one reaction at point A. So as you can see, RA equal to 1. And I have two reactions at point B. So RB is equal to 2. Instead of R, I have to put the summation of these reactions that we had in the structure, RA plus RB, which is 3. So R will be 3 in this equation. The other value or the other parameter that we have is EC, which is equations of condition. As you may remember, during the presentation files, we said that if we have a roller in the middle of a structure, EC or equations of condition are equal to 2, because for that roller we can say summation of forces in X is equal to 0 and summation of moments about the roller is equal to 0. So whenever we have a roller in the middle of a structure, we can say EC is equal to 2 for that roller. And whenever we have a hinge in the middle of a structure, EC is equal to 1, because the additional equation that we have for that hinge is the summation of moments about the hinge is equal to 0. In this example, we don't have any roller or hinge in the middle of the beam or along the length of the beam, and the beam is continuous. So EC is equal to 0. Now I can return the values of R and EC to this equation over here. And once I do that and calculate the value of I, the value will be equal to 0, which means that the structure is stable and determinate. So the second step is done. We could understand whether the structure is determinate or indeterminate. Now that we know the structure is determinate, we can find the reactions based on the equations of equilibrium. So let's write those equations and see how we can use them for finding the reactions. When we are talking about the equations of equilibrium, we are referring to these three equations. As you can see, the first one is summation of forces in the horizontal or X direction is equal to 0. This is this equation. The second equation is summation of forces in the vertical or Y direction is equal to 0. And the third equation is summation of moments about a point, in this case point A, is equal to 0. This is the structure that I'm talking about, and I'm going to solve these equations for this structure. The first one was summation of forces in X direction is equal to 0. So this is the X direction, and I need to find all the forces that I have in the horizontal or X direction. This reaction at point A, this is inclined, which means that it has both X component and Y component. These 12 Gibbs has an angle to the horizontal axis, so it also has X component and Y component. and I also have Bx, the x component or horizontal component of the reactions that I have at point B. So let's put these in this equation. Ra, reaction at A, and I need only the horizontal component, so multiplied by 3/5, right? Based on the statics, you know that if a force had an angle to the vertical or horizontal axis, we know how to find the x component or the horizontal component. If you don't remember that, please go down to the end of the fourth example. Yes, over here you can see I have a review note to show you how to find the components of forces. For example, if a force has an angle to the horizontal axis equal to theta, the x component or horizontal component is f multiplied by cosine of theta, and the y component is f multiplied by sine of theta. So these are the equations that we need to use for finding the x component and y component of a force when it has an angle to the horizontal axis. In cases where we don't have the angle, but we know the size of the sides, I mean, for example, let's say I know this side is equal to A, and this side is equal to B, and the dimension over here is equal to C. In such cases, if I want to find the x component of the force, or fx, we can say f multiplied by A over C, or the ratio of horizontal side over the C over here. And if I want to find the vertical component, I have to just multiply the force by the vertical side over C. Alright? So based on these two equations or these two situations, we can simply find the horizontal component and vertical component of forces that we have in structures, and it will make the situation easier for us when we have inclined forces in the structure. So let's go back and look at the situation that we had in our problem. It was the problem. I was writing this equation, summation of forces in x direction is equal to 0. And as you know, I'm always assuming for x direction, the positive direction is toward the right direction, or as you can see over here, this direction is positive x toward the right direction, and for vertical direction, the positive side or the positive direction is upward. And about moments, we are going to always add positive direction is always counterclockwise, and you will see how these work in solving the example. But this is the equation, summation of forces in x direction is equal to 0. So positive is in the right direction. The x component or horizontal component of this reaction will act in the x direction or to the right. So that is positive, and the value is Ra multiplied by 3/5, the horizontal side over the side that represents the direction of the force. So Ra multiplied by 3/5, that is the horizontal component of Ra. Then I have this 12 kip force, which is in this direction, and as you can see, the horizontal component will be to the left, which means the negative direction. So I have to say minus 12 multiplied by cosine of the angle that we have, because if I multiply it by the cosine, I can find the x component. If I multiply it by the sine, I can find the y or vertical component. So minus 12 multiplied by cosine of 60, and we also have this horizontal reaction or horizontal component of the reaction at point B multiplied by plus Bx. And this is positive because this is in the right direction, or the direction of this reaction is toward the positive x. So we could write the equation for x components or horizontal components. As you can see in this equation, I have two unknowns, which means that this equation is not going to give me the unknown values. Let's write the equation for vertical direction and see what is the situation over there. So summation of forces in y direction equal to 0. And I'm going to assume positive is upward. In that case, if you look at the beam, as you can see, this reaction at point A has a vertical component, and that will be RA multiplied by 4/5. The vertical side over the side that is to the direction of the force. So the vertical component will be the vertical side over the side that is to the direction of the force, right? That will be RA multiplied by 4/5. So let's see how we can write it in the equation. Summation of forces in y direction is equal to 0. So RA multiplied by 4/5. Then we have this force over here, and it is downward, or it is directed to the negative y direction. That's why I have to say minus, as you can see in the equation, minus the vertical component of the force, which is 12 multiplied by sine of the angle, or sine of 60. That is this term over here. And then we have the vertical component at point B, so that will be By. And finally, I have a 6 kip force at the end, which is downward, so that should be negative. Over here, you can see these in the equation. RA multiplied by 4/5 minus 12 sine of 60 plus By minus 6 equal to 0. So again, I have two unknowns in this equation. And if I look at the first equation, you can see in both of these two equations, summation of forces in x and y equal to 0, we have three unknowns, RA, Bx, and By. And based on the knowledge that we have in mathematics, we know that having two equations and three unknowns will not give us the value of the forces. So let's write the third equation, which is summation of moments about a point in the structure is equal to 0. This is the third equation. And as you can see, I'm going to calculate the moments about point A. Summation of moments about point A is equal to 0. And in my solutions, I always assume the positive direction for moment is counterclockwise. As you can see, I'm writing it over here. Summation of moments about A is equal to 0. Positive is counterclockwise. And based on that, I can find the moments. So let's see how can I find the moments about point A. Reaction itself does not have any moment about point A because the force is exactly located at the point. If it is the point, the force is applied exactly on the point, and it does not create any moment. Moment is created whenever we have some distance between the force and the point where we are calculating the moment about. So reaction of A or RA does not create any moment about A. This 12 kip force, it has a horizontal component and a vertical component. The horizontal component will not create any moment because it is concurrent to the point. it exactly hits the point and there is no distance between the force and the point. So that does not create any moment. But the vertical component, as you can see, has 10 feet distance to the point. So the vertical component will create a moment and the direction will be clockwise, right? 12 keep and the direction will be clockwise. If you just multiply the vertical component by the distance, you can find the value of moment. That is what we have over here. Minus is because the moment will be clockwise and the value is 12 multiplied by sine of 60. That is the vertical component of the force, and now I have to multiply it by the distance, which is 10 feet. Minus 12 sine of 60 by 10. That is the moment because of the force that we have over here. Then I have to find the moment because of this force. As you can see, at point B we have a vertical component and a horizontal component. The horizontal component does not create any moment about point A because it is crossing the point. It is concurrent to the point. There is no distance between the force and the point, so it does not create any moment. But the vertical component, you can see it has 20 feet from the point, which means that it will create some moment. And that moment will be By multiplied by 20. And the direction is counterclockwise. As you can see, it creates the moments counterclockwise, and thus that is positive. Plus By multiplied by 20, or 10 plus 10 is just this distance over here from By to point B. And finally, I have this 6 keep force over here. It has 25 feet distance to point A, and the moment will be counterclockwise, right? The moment will be counterclockwise, and the value will be 6 multiplied by 25. So I'm going to write it down over here, and as you can see, minus 6 multiplied by 25, or 10 plus 10 plus 5. All right? So this is the equation for moments. As you can see, in this equation, the only thing that is unknown is By. So I can simply use this equation and find the value of By. If I do that, you can see By will be this equation, and solving this gives me By as 12.696 Q. The value is positive, which means that the direction of the force is similar to what we assumed when we were drawing the free body diagram. When I was drawing the free body diagram, I didn't have any information about these forces. So I just assumed RA is in this direction, By is in this direction, and Bx is in this direction. But when we solve the equations and find the values, if the values are positive, it means that our assumption is correct and we don't need any modification. But if I find a negative value, it means that my assumption was wrong and the direction is the other way. For By, I assumed it is upward. I solve this equation. The value is 12.696 keep. Since it is positive, it means that my assumption was right and By is upward. Now I can return to equation 2, this equation. Because now I have By, I can simply put the By instead of this parameter over here and find reaction at point A. That is what is happening over here. I return to equation 2 and put the value of By in the equation. As you can see, the value of By is over here. So I put the value of By and then calculated everything. The value of Ra is 4.62 keep, and this is positive, which means that this reaction is in the same direction as we assumed, perpendicular to the plane of the support, roller support. Now it can be either in this direction or in the opposite direction and downward. But since the value that we got is positive, it means that my assumption was right and it is toward the up, it is upward actually, right? Because it can be either upward or downward. The value that I found is positive, so it is upward. We could find RA, and that was 4.62 kips. The only thing that is left is Bx in the first equation, or in the equation that we wrote for summation of forces in x direction equals to 0. I have to just put the value of Bx over here. We found that as I'm sorry, we have to just put the value of RA over here. Bx is the thing that we don't know yet, but we found RA as 4.62. So if I just return this value over here, you can see Vx will be equal to 3.229 kip, and this is positive, which means that my assumption was right and it is directed to the right, which is the positive direction for x axis. As you can see, I just wrote the first equation again and put the value of RA, and all I need to calculate is Bx, and that value was 3.229 kip. As you can see, by writing these three equations of equilibrium over here, I could simply find the reactions that we have in this B. By this step, and at this moment, we can say the solution is done. We could find the reactions, but I always have one extra step, which is checking the values, and for that we can write additional equation, and that equation can be any equation, doesn't matter which equation it is, just one additional equation to check if the values are right or not. In this case, I wrote the additional equation as summation of moments about another point other than point A that I used earlier. About another point is equal to 0. So over here, I said summation of moments, this time about point C equal to 0, which is right because point C is a free point. As you can see, there is no reaction or anything. So summation of moments about this point is equal to 0. And now I'm going to put RA and reactions at point B as the values that I found in the equations. If I put those values and calculate everything, and at the end I find the summation of moments at point C equal to 0, then it means the values are correct and my solution was right. So over here you can see summation of moments about point C is equal to 0, positive counterclockwise, and I just put the values over here. So let's go back and look at, this is point C, and I'm calculating of the summation of moments about this point. As you can see, we have this RA. The x component does not create any moment about point C because the x component will cross the point, right? But the vertical component, or the component in the y direction, has 25 feet distance to point C, so that will create a moment, and that moment will be clockwise, right? So RA multiplied by 4/5, which will be the y component or the vertical component, and then multiplied by distance will be the moment because of this RA. Then I have, and that should be negative because that is clockwise. Then I have this 12 kip force. The vertical component of this force will be 12 multiplied by sine of 60, right? We talked about it and I showed you the review note at the end of example 4. But that is the vertical component of this force. So if I calculate that and use that, that will be the vertical component of the force, and the distance to point C will be 10 plus 5 or 15 feet. So 12 multiplied by sine of 60 multiplied by 10 plus 5 or 15 will be the moment because of this force, and that should be positive because the direction of the moment will be counterclockwise, right? It is counterclockwise. Then I have the moment because of reaction at point B, and this moment will be just By. Bx is crossing the point. As you can see, there is no distance between Bx and the C, so there is no moment because of Bx, but By has 5 feet distance to point C. The moment will be By multiplied by 5. And it will be negative because it will create a clockwise moment. So those are the terms that I write in these equations. As you can see, By is negative because it created a clockwise moment. Instead of these values, these parameters, I have to put the values that we found in the equations. Ra, we found it as 4.62. By, we found it as 12.696. I just put the values, and then you can see final result is a very small value, 1.315. That is because of the rounding errors that we have in the solution. You know, each of these values, they are just rounded to this value. If I wanted to find or use the very accurate value, I should have included more digits after the point. But because I rounded these values in my calculations, at the end there is some error. But as you can see, it is very close to 0. So we can say it is almost 0 and the solution is fine. If you repeat this example and just use the very exact values that you have in your calculator instead of rounding them and then using them in other equations, you will see that this error will be much less than what I have over here. That was the first example, and let's see what we have as the second example. All right, let's see what do we have for the second example. Over here you can see we have a beam with fixed end at the right side, and that's the only support that we have for this beam. So it's only fixed at the right, and it is called a cantilever beam. So we have this beam, fixed end at the right, and the loading. The first step was to draw the free body diagram. As you can see, for drawing the free body diagram, I have to draw the beam. I have to put the forces as shown in the example or in the problem. And the only thing that I need to add to this drawing is the reactions. And reactions are these 3 at the end of the beam. You know, when we were talking in the presentation file, we said whenever we have a fixed end or fixed support, we have 3 reactions. One reaction in the vertical direction, one reaction in the horizontal direction, and one bending moment. As you can see, I'm showing these reactions like this over here. And again, like the situation that we had in the first example, at this moment, we don't know the direction of these forces in the reaction. That's why I'm going to just assume some direction, and I usually assume the positive direction. So whenever I'm drawing the reactions and putting the reactions in their place and I don't know the values, I'm going to just assume the positive direction. So as you can see, I assume By to be in the positive void or vertical direction. I assume Bx to be in the positive x direction, or I assume the positive bending moment to be counterclockwise, as I always assume positive moments are counterclockwise. So these are the reactions, and this is the free body diagram of the beam. Now we can move to the second step, which was finding the situation about determinacy or indeterminacy of the beam. As you can see, this is the beam. For finding the situation about determinacy, we need to know the reactions and EC, or reactions and EC equations of condition. Reactions are only these three, so R is equal to 3, EC is equal to 0 because I don't have any hinge or roller during the length of the beam. If I had, I would include those values as EC. As you may remember, I said whenever we have a hinge, EC is equal to 1. Whenever we have a roller, EC is equal to 2. But over here, I don't have any of those, so EC equal to 0. And now I can simply look at this equation that we had about stability and determinacy, putting the values in the equation. R equal to 3. That 3 value is the same, and EC equal to 0. The final value will be 0, which means that the structure is stable and determinate. It is good because when it is determinate, it means that we can use the equations of equilibrium to find all the reactions. So let's write those equations of equilibrium and see what are the situations and reactions in the beam. The first equation is summation of forces in X equal to 0. Let me go back and take a look at the beam. This is the beam. Summation of forces in X is equal to 0. Let's see how many forces we have in the X. That's just Bx, right? So Bx is equal to 0. Simple and very straightforward. Then we have summation of forces in the vertical direction equal to 0. As you can see, I have to look at all the forces that I have in vertical direction. I have this uniformly distributed load. As you know, the amount of load that we have under uniformly distributed loads is the area under the load. So that will be 15 multiplied by 6, right? 15 multiplied by 6, and that is negative because it is downward, and the positive direction that we assume is upward. I also have 160 over here, and the only remaining thing is By or reaction at point P. So minus 15 multiplied by 6 minus 160 plus By should be equal to 0. As you can see, this is the equation. And based on this, we can simply find the reaction, the vertical reaction at point B, which is 250 kilonewton. So I could find Bx, I could find Bi, and now I can find the moment at point B by saying summation of moments at point B equal to 0. Right? If I do that, I have to just find the moments about point B. I have this moment, which is clockwise, so I have to say minus 400 kilonewton meter. Then I have this distributed load, which I can put a single load in the middle of it, and the magnitude of load should be area under the uniformly distributed load. So that will be 15 multiplied by 6, located at 3 meters from the point A over here. Then the moment will be 15 by 6, and the distance will be 4 plus 4 plus 3. As you can see, this is the situation over here, and this is positive, as you can see over here, because it is creating a counterclockwise moment. Then I have this 160 kilonewton force, which creates again a counterclockwise moment, so that will be positive, and the amount of moment will be the force, which is 160 multiplied by the distance, which is 4 meters. And the only remaining will be the moment at B itself, which is MB, and that is counterclockwise, so positive. So these are the values in the third equation, summation of moments about b equal to 0. The only unknown is mb, and if I solve the equation, we can see the value will be negative 1230 kilonewton meter. When it is negative, it means that my assumption was right, and the moment over here is actually clockwise instead of counterclockwise. That is the meaning of this negative over here. So, as you can see, the direction that I always mention in the parentheses after the forces means that the correct or the actual direction of the moment or force. It is negative. I assumed at first it is counterclockwise, but I found it as negative, which means that the moment is actually clockwise. As you know, there is one extra step in my solutions, and that is the check, which means that I'm going to check whether the values are calculated correctly or not. And for that, I'm going to calculate the moments about point A. It does not give me any additional information. I just want to see if these values that I found as the reactions are accurate. So summation of moments about point A this time is equal to 0. A very similar procedure. I just need to put the value of by and mb in the equation. As you can see, this is the equation. This is the equation. And if I just calculate all of these values, the final value is 0, which means that the calculations that we did earlier for finding the reactions are correct. And through this procedure, we can say we could solve the problem. Okay. Let's take a look at the third example and see how we can find the reactions for this frame that is shown over here. As you can see, this frame is carrying two uniform loads, two distributed loads. One of them is in the horizontal direction, as you can see, 2 kilonewton per meter from left to right. And the other distributed load is this one, which is in vertical direction, and it has a trapezoid shape. And in terms of the support, we only have a fixed support over here. So for beginning the analysis, the first step was to draw the free body diagram. That is not difficult because the loading is given. All I need to do is to add the reactions, and those are 3 reactions over here. One in X direction, one in Y direction or vertical direction, and one bending moment. We can see that over here. These are the reactions, and I can simply move to step 2, which was finding the situation about determinacy of the structure and see whether it is determinate or not. So if you look at this part, you can see I put the R as 3, the reactions at point A. EC is equal to 0 because we don't have any any hinge or any roller in the structure. As you remember, those are the conditions about equations of condition, or the conditions that we have for having a hinge or a roller inside the structure. Over here, as you can see, the structure is continuous, so EC is equal to 0, and all I need to do is to return these values into this equation, and once I do that, I will be equal to 0, meaning the structure is stable and determinate. So we could find the free body diagram. We could see that the structure is stable and determinate, and now I need to start analyzing the structure for finding the reactions. And for that, we need to write the equations of equilibrium. Before doing that, let's take a look at this distributed load over here. As you know, whenever we have a distributed load, we can put a single force instead of that distributed load, and the magnitude of that force will be the area under the distributed load. And the location of that force will be the centroid of that distributed load. Over here, I have a trapezoid, and since it is not common to know the centroid of a trapezoid, I'm going to consider it as two separate shapes. One is a rectangular shape and the other one is a triangular shape. And then I can say these two loads are working together and adding to each other in terms of the loading that we have on this portion of the frame. This is called superposition. The rule or the theory of superposition tells us that we can apply loads in different amounts or in separated amounts in a way that the summation of those separated amounts is equal to the total load that we have on the structure. Of course, there is a very basic assumption behind this theory, and that is linear behavior of structures. The discussions and the details about this theory is not part of this course, but I just wanted to give you the name of this approach that I'm using in this example. Instead of having this total trapezoid, I'm going to consider a rectangle and a triangle on top of it in terms of the loadings that we have on this frame. So, considering these assumptions, let's see how we can find the reactions in this frame. At first, I have to write the very famous equation about forces in the horizontal direction or x direction. Summation of forces in x direction is equal to 0. I'm always assuming positive is to the right, like this. So I can say AX, reaction at point A in the x direction, plus this load which is in the x direction, and it should be positive because it is to the right. And the force that we can get from this loading is area under the distributed load, which is 2 multiplied by the length, which is 15. And that's it. I don't have anything else in the x direction. So 2 multiplied by 15 plus AX equal to 0, which means that AX is minus 30 kilonewton to the left. I'm concluding this, or I can say this is to the left direction because the value is negative, meaning the assumption that I had about the direction at first is wrong, and it should be exactly in the opposite direction, and the reaction of A in the x direction is to the left. So, based on summation of forces in x direction, I could find the reaction, the horizontal reaction at point A. Now I can write this equation for the vertical direction. Summation of forces in y direction is equal to 0. And if I do that, we can say AY, this reaction over here, minus the rectangular distributed load, which is 2 kilonewton multiplied by 9. That is for the rectangular shape. And now I have to include the triangular shape, which is area under the triangle, which is 3 multiplied by 9 divided by 2. This is over here. So, vertical direction at A or AY minus 2 multiplied by 9, which is area under this triangle, minus 3 multiplied by 9 divided by 2, area under this triangle over here. If I calculate this, we can see AY, or the vertical direction at point A, is equal to 31.5, 31.5 kilonewton. And this is positive, so my assumption was right and it is upward. the only remaining thing is summation of moments about point A. Summation of moments about point A. And this will help me find the bending moment at point A. As you can see, at first I didn't know the value of moment, so I just put the MA over here, and the direction is, by assumption, in the positive direction, counterclockwise. If we get a positive value, it means that the assumption is right. It is counterclockwise. And if I get a negative value, it means that this assumption is wrong and it is the other way. It is the other way or clockwise. So let's write the equation. Summation of moments about point A is equal to 0, positive counterclockwise, which means that MA, this moment, minus the moment because of this distributed load, which will be 2 multiplied by 15. That is the force representing this uniformly distributed load. And the location of that force will be at the center of the distributed load, which in this case it is exactly over here. So we can say 2 multiplied by 15, that will be the force representing this uniform load, and the distance will be 15 divided by 2. And the sign of this moment is negative. It is negative because the moment that this is causing about point A is clockwise. So minus 2 by 15 multiplied by the distance from that force to the point that we are considering, which is point A, that is 15 divided by 2. So let's see what other forces we have over here. We have these vertical distributed loads at the top. I said instead of this trapezoid, I'm going to assume 2 distributed loads, one in rectangular shape and one in triangular shape. For the rectangular shape, we can say the load is equal to 2 multiplied by 9, and the distance from centroid of this distributed load to point A is 9 divided by 2. I am finding the centroid of this triangle over here. And then after this, we can consider this triangle. At first, I considered this rectangle, this one, 2 multiplied by 9 multiplied by 9 divided by 2. And now I'm going to consider this triangle over here. Right? This triangle at the top. For this one, the load will be area under the triangle, which is 9 multiplied by the amount of load, which is 3 divided by 2. And this is located at the centroid of this triangle, which is 1/3 of the length, and it is located closer to the larger side, which will be 3 meters from the right end or 6 meters from the left end. So I have one load over here because of the rectangular load and one load over here because of the triangular load. Those are calculated over here. 2 multiplied by 9 multiplied by 9 over 2 is because of the rectangular shape. And 3 multiplied by 9 divided by 2 is the load because of the triangular shape. And 2/3 of 9 is the distance from centroid of the triangle to point A over here. This is the triangle. Centroid is over here. And the distance from its centroid to point A is 2/3 of 9 or 6 meters to the left. If I wanted to find the distance from centroid to point B, that would be 1/3 of the length or 3 meters. So the term in the parentheses is the amount of load, and this term over here is the distance from centroid of the load to the point that I'm calculating the moment about. This is the equation. And now if I solve this equation, I can find the value of MA as 387 kilonewton meter, and the value is positive, which means that my assumption is right and the direction is counterclockwise. So we could find the horizontal reaction at A, we could find the vertical reaction at A, and we could also find the bending moment at point A. I have this extra step, which is just checking whether the values are correct or not, and for that I can find the summation of bending moments about another point, which in this case we can say point B. Summation of bending moments about point B equal to 0. That will be one moment because of this rectangular loading, one moment because of this triangular loading, one moment because of this uniform load over here, and of course the moment because of AX, AY, and MA. Those are all calculated and included over here, and if I calculate this calculation or perform this calculation, you can see the final value is equal to 0, which means that my calculations about AX, AY, and MA are correct, and we could correctly find the reactions in this frame over here. Please pay attention to this calculation that I have over here, because when we are putting the sign of these moments, we have to look at the direction of the moment and also the value that we got as the reaction. For example, if I look at over here, I have this AX, and this AX is creating a counterclockwise about point B, so the moment itself should be positive. But since the value of AX that I found over here is negative, I have to put minus 30 multiplied by 15. And about this force AY, the moment that it is creating about point B is clockwise, and thus it should be negative. And the value of AY is 31.5. The procedure is very simple. All you need to do is to look at the moments and directions that you have for the forces and bending moments, and make sure that you are using the correct sign for the values that you have in your calculations. And if you pay attention to these, it shouldn't be difficult to solve examples. I will leave the rest of the time for you to take a look at these examples and solve them again for yourself. If you have any question, you can use the link that I provided for the WebEx meeting, and we can question and answer over there with more details. Thank you very much, and take care.